Okay, we're looking at the 1982 AP Physics C Mechanics problem, but you see this problem in all college physics books. So you have a block and it's at rest and it comes down and it actually compresses the spring. So this is a classic physics problem. So a 20 kilogram mass released from rest slides 6 meters down a frictionless plane inclined at an angle of 30 degrees with the horizontal and strikes a spring of the spring constant. And again, we want to circle all the important information as shown in the diagram. Assume the spring is ideal and that the mass of the spring is negligible. All right, so the first part says determine the speed of the block just before it hits the spring. So this is conservation of energy. Whenever there's a change in height, okay, so whenever we have a change in height, again, we're going to use conservation of energy. So we can say the total energy here is equal to the total energy here is equal to the total energy here. Any place, the total energy is going to be the same. So what makes this easy is that at the top, it's all gravitational potential energy. So since it starts at rest, and again, when you read the problem, there's key information. That means the initial kinetic energy is 0. So what they want us to do is they always want to see a statement with conservation of energy. So I can say that, so it says just before it hits the spring, I'm going between here and here. So this is the top and this is before it hits the spring. So I'm going to say U naught plus K naught is equal to UF plus KF. And then again, this is the gravitational potential energy because it hasn't hit the spring yet. So again, at the top, because it starts from rest, this is 0. Whenever I use conservation of energy, I always want the bottom on my frame of reference to be base level. Okay, so I'm starting off here. This is my original height here. And then I'm going to this point right here. Okay, so the gravitational potential energy is mgh plus 0 is equal to, since this is my frame of reference, okay, since that's my frame of reference, the gravitational potential energy is going to be 0 because that's my frame of reference, plus 1/2 mv squared. Now to make the algebra easy, I can cancel the m's. So I'm going to have GH is equal to 1/2 b squared, and then I'm going to rearrange the equation to solve for the unknown in terms of the known. So I'll multiply both sides by 2, and then I'll take the square root of both sides. So I see that V is equal to the square root of 2GH. Why do I bother doing all this algebra? Because if I don't, I might forget to take the square root at the end. So this is going to be 2. And if I want to use 10 or 9.8 times the height. Now this is the hardest part of this problem. So remember, when we're doing gravitational potential energy, we're talking about the height here. Okay, so this from here to here, so we're going from here to here, this is 6. But that's not the height that we're going to use, and that's the mistake that most people make. So we actually want this vertical height here. Okay, so this is where now I take my knowledge of geometry. So if this is 6, and I know this is 30 degrees because it's similar triangles, this is what I want to find, which I'm going to call H prime. So to find H prime, again, you can write your definition. I see it's opposite that. But if I'm not sure, you know, I know that sine is opposite over hypotenuse. So sine of 30 is equal to h prime over 6. So h prime is equal to 6 sine of 30. And we know that's half. So this comes out to be 3. So now I know that this is 3 meters. So this is probably the trickiest part of this problem, is making sure you don't make a mistake and you use the correct height for gravitational potential energy. So when we do this on our calculator, we get 7.7 meters per second. All right, part B, and again, this is a classic physics problem with a block starting from rest, sliding down an incline and hitting a spring and compressing it. All right, so then part B says, and again, the problem is we have to keep looking at this picture. It says, determine the distance the spring has compressed when it comes to rest. So now it's going to be stopping. Now, again, I can pick any 2 points I want to figure that out. So when the spring is compressed, now we have the potential energy that was stored in the spring. So again, we're going to use conservation of energy where that comes to rest. And again, we're going to call where it comes to rest phase level. That's going to, so if this is compressed, let's say down to here, that's going to be our frame of reference. So again, you can pick any 2 points. I would always go from the top to wherever, because at the top, this is super easy because it's just gravitational potential energy. So again, the total energy at the top is going to be equal to the total energy at the bottom. Now, what I could have done before is say the sum of all the potential energy, which would be like UG naught plus US naught plus K naught is equal to UGF plus USF plus KF. So this is the gravitational potential energy, and then this is the potential energy stored in the spring. So first of all, this and this is 0 because I know at the top it's just MGH. And that's why I use the top as one of my frame of references, because it's easy. When it's at rest, it's just all gravitational potential energy. Okay, so now on the other side, this is going to be 0 because this is going to be my new frame of reference. I'm going from here to wherever the spring is compressed. So this is 0. The potential energy is 1/2 kx squared plus 0. Now again, this is the part that has to do with the geometry. So I have this distance here, which I know is 6. Now it's going to be compressed some distance, which I'm trying to find, so I'm going to call it x. Okay? So if this is x, now I don't know what is the height from here to here. I already know that this is 8. So remember, this h we did before was the hypotenuse times the sine of 30. So if this hypotenuse was 6, and now it's going to be compressed some distance x, it's going to be 6 plus x. Oh, I'm sorry. Well, I could say d plus x. So d plus x, because that's what that distance is. So 6 plus x sine of theta, which is sine of 30. So now when I do this, this is going to be mg d plus x. I'll just write the d plus x, because a lot of times they might be in terms of variables. Sine of theta is equal to 1/2 kx squared, and now we're solving for x. So now when I simplify this or substitute in my values, I'm going to have 20 kilograms times 10 meters per second squared times 6 plus x times the sine of 30 is equal to 1/2 200 times x squared. Now looking at this, even after I multiply all this out, I'm going to have an x and an x squared. So when I do that, the only way to solve this is to do the quadratic equation. So when I multiply this all out, 20 times 10 is 200 divided by 2, because sine of 30 is 0.5. So that would be 100. 6 plus x is equal to, and when I multiply this, 200 divided by 2 is 100. So that's going to be 100x squared. So now I'm going to pull this out because I don't want to make a mistake. This is where I don't try and do, people understand the physics and then they make algebra mistakes. So I'm going to have 600 plus 100x is equal to 100x squared. So I can divide by 100. So then I'll have 6 plus x is equal to x squared. So in quadratic form, you would have x squared minus x minus 6 is equal to 0. Now, if you have a program built in your calculator, you can do that to solve for the roots. If you want to solve for the roots, this one isn't really that hard, x minus 3 and x plus 2. So you're going to use the positive root. So x is going to be plus 3 meters. So on this, the most difficult part was probably the height from here to here. But once you see it as the triangle, it makes sense. And then, of course, you have to do the quadratic. All right, let's look at the last part of this problem, part C. Part C says, is the speed of the block a maximum at the instant the block strikes the spring? Justify your answer. So we know with Hooke's law, F is equal to minus kx. So the spring force, if you look at this equation, the spring force increases as the compression of the spring increases. How do we know that? Well, when you look at the equation, you can see that they're directly proportional. So the maximum velocity is going to occur when the acceleration is 0, which would mean that F net is equal to 0. So the answer here is no, because at the instant the block strikes the spring does not yet exert a force. Okay. So again, with this, the hardest part would probably be the middle part, part B, where I'm doing conservation of energy between this point and this point. But again, it might be good to use a different color because I'm going from here, let's say we don't know what it is, I put here, I'm finding this height here. And then that's why this is 6 meters plus x, because this, again, this is a right triangle and they're similar triangles. And that's how we do that.